That's only 30. So where do we get the last 2? Again, converting byte to word. You're going to say, you know what, I'm totally confused. That's okay, because you can try this out. Let me give you one example before extra credit. Let's take this one. See, this is what you want to do. Take every one of these things, put it in Mars. How long does it take? Well, not that long. But then you totally understand how the instruction works. So let's just say bye to that. Is there anything else we need? We need to set the settings for memory configuration. I want the text to start at address 0. Okay. And then apply. And maybe we just put 3 instructions so we can see something going on. ADD, T0. These are dummy. Okay, they're dummy. I don't really care what they are that much. And then ADDI. All right. All right. Oh, sorry. See? Okay. And then if I haven't made any syntax errors, we can assemble this one. Assemble with errors. So what am I doing? Help me. Add. Looks okay to me. Oh, jump to 8. 8's not a label. I have to have a label. So at 8, which is going to be here, we're going to show you why. I'm going to call this label. This is in between machine code, which we're going to see in the next slide. It's going to convert label to 8. Why? Because it's the 8th byte address. But remember, the programmer uses a logical label, logical address. Give me a colon. Colon makes it a label. Parsley makes it fancy. I had a t-shirt with that one time. All right. Wow, it worked. Look inside here, right? You said jump label. Yeah. It converted to jump address 8. What are the bits of the instruction? 0, 8. You're going to say, well, wait a minute. 0, 8's not the opcode for jump. But remember, that's 6 bits. This is representing 8 bits. Can I see it? Yeah, you can see it. You got to know your bits. See, this is what? 2. 02 hex is the same as 02 dec. It's 2, but as 2 hex digits, that's a 0, and then what? The next 4 bits is a what? 8. Give me your attention for 10 more seconds. Where are we? Mars. We're in Mars. Then what? This is the next thing you're going to jump to. See? This is the 3rd instruction. We talked about encoding instructions, obviously, in this module, but specifically branch and jump. So we had branch was a relative address. And jump, we said, was absolute. Anybody, what's the difference between 1 point extra credit? Absolute versus relative address. Raise your hand. I'll take it. Yes, sir. What's your name? Seth. Seth, you're just in my office. Seth, I can't see you back there. So what's the difference between relative and absolute address?
Relative is referencing another point, and absolute is referencing 0.
Yeah, so absolute references the axis origin, right? And relative is based on your current location. So to get your 1 point, from the processor's point of view, what is the current location? Where do we look to find that? Maybe, but there's a certain register. I'm going to give it to you, but what's a certain register that tells us the current location? And you're on the spot. Sorry, didn't mean to put you on the spot. So help them out. Anybody?
PC register.
Program counter. Program counter. tells us the current location. Okay. So what's the difference between what we saw with branch was a program counter and absolute? Absolute, we're going to have every bits of the address except what? A few bits, right? So we have 6 bits for opcode. We have 32 to start with, leaves us 26. We have to create a 32-bit address out of 26. So what was the formula we discussed last time? Take the 26 bits, shift it left 2 bits, multiplies it by 4, which converts actually to the word offset. That's interesting. And then we only have, what, at that point, 28? Yeah. So we need to get to 32, so take 4 from the PC. So the thing to think about this process is that the upper 4 bits, it's within the local area wherever the PC was. So even though it's absolute within some segment of memory. So let me ask you this. If we have 32 bits, what's the maximum addressable space that a MIPS processor can reference in bytes? Memory is byte addressable. So you have 32 byte address bits. What's the address range in bytes? 4 gigabytes, yes. So the way to think about this is that these upper 4 bits, which we're seeing in green here, is breaking that 4 gigabyte range into how many segments? Well, you have 4 bits. So let's draw a picture. So 4 gigabytes range. That's the whole memory map, right? And we're going to partition this. See, because look at these addresses, right? This is the address. Usually right over here, right? This is address 0. All zeros, right? And this is to 1. When do we switch these upper, the 4 bits? When does the upper 4 bits switch to 1? Well, after all these bits go to 1, then it goes to 0, wraps around, right? So if I number, I'll make it easier. If I number this segment 0, this segment 1, this is going to be the next segment, 0, 0, 1, 0. What does that mean? These are the green bits, right? 0, 0, 1, 0 comes in. What's X, if X is the largest segment number? Yeah, you got it. Okay, this is segment number 15. So the way to think about this is you can jump within any of 15 segments of the entire addressable space. So it's not completely absolute, but we call it absolute. It's not relative because its relative has to use the PC, but we can get almost anywhere we want to go, right? So the way to think about this is we do the same thing with in the old days when we had phone numbers, right? You had area code. Area code says, well, within this region, here's the number. Address is the number, right? So you can call anybody within that area code. You can branch to anywhere within the area code. Okay. That's absolute, though. It's absolute because it doesn't matter what the PC contains versus branch, right? So here we can see direct address for jump. Direct into absolute is 2 words for the same thing. Relative for branch. And here's the encoding. I guess we said 6 and 26. And here is what we just said. There's an operator you can learn. It's called concatenation. Concatenation means to append 2 bit strings. So if I concatenate, right? 2 strings. If this is 1 string and this is another string with a space, I concatenate them. Okay. I'm going to write these as 1 new larger string. These are characters. This is concatenating bits. So I concatenate bits 31 through 28 inclusive, right? Whatever the address field was, it's called jump target on the testing reference sheet, times 4 because I've shifted it to left. How many bits? Let's multiply by 4. I shifted it 2 bits. Okay. So let's try an example. Assume that the program counter contains this. Is that really relevant? Maybe, maybe not, right? We're going to see. Because remember, it's absolute. Relative, for sure, we need it. So sometimes there's information in a problem may not necessarily contribute to the problem. Let's take a look. So jump instruction is going to be executed next, which is jump label. Write a machine code for this instruction. If the label has address as follows, this is a byte address. Okay. Express your answer in hex. So before we solve this problem, what is this? This is where we want to jump to. That's the address expressed in binary. Can I express this in hex? Yeah. This is A, 0, 9, 8, 7. Yeah. Where are we right now? Well, just to see, right? This is A, 0, 0, 0, 0, 0, 12. Okay, C. So, question is, I'm asking you to write these bits. What are those bits? Those bits are the encoding, right? Encoding of the jump instruction. I put an announcement over the weekend. These things change over time, new processors, we add new instructions, more registers, we change the encoding. So Intel has some new encodings. You can read that there. It's just information on the announcement. But here we're looking to say, give me the bits when we execute this instruction that the PC fetched from memory. It goes into the processor, it's going to turn on and off the circuits. What circuit? Well, we're going to design more, but we're starting to see when the bits come in, they have jobs. Some are telling us to adjust the program counter. Some of us, some of those bits, some of those tasks here, some of us that we're going to consider will actually change control signals, turning on and off. Okay. Elements of the data path. So we're asking you to write those bits for that particular instruction. This one's pretty easy. We have 6-bit op. It turns out that the opcode for J instruction is 2. It comes from the table. The 26-bit address is the word address that you want to jump to. Well, it says we want to jump to this address. So label, specified by the programmer, right? It's a label. It's a virtual address that gets converted to a number. That's the number that we want to jump to. But we have to write this. This is 32 bits. We have to write this as 26 bits. So we do need, right? We do need the upper 4 bits. Even though it's absolute, right? Because we're going to have to use that. So how do we get to 26 bits? To get the 26-bit address, we're going to ignore the first 4 bits because we're already in that range. That means we're in the right area code. That means we can call with, see, in Orlando we have 10-digit dialing, actually. Anybody ever live any place else in the country? Yeah. Did you have 10-digit? Huh? Did you have 10-digit dialing where you lived? Yeah. You did, okay. It's kind of actually the exception. When it first came out, Orlando actually was the first region that adopted the 10-digit dialing. Because other places you go, used to go, you want to call somebody that says 7-digit, you don't have to put the area code every time. But here we have an overlay. So you have a 407 and 312. And now all these, right? But, so the good news is we can jump there because we're in the same area code. So what we have to do is just get the 26 bits. To get to 26, we're going to take this. If this is going to be shifted left to make that, it must have been shifted right to generate it. So I'm going to take that, see that string? You can see it's shifted right 2 bits. Why did I shift it right 2 bits? Because the circuit is going to take it and shift it left at the time it's executed. So it means to encode it, I want to shift it right. It's just like, you know, if you're going to add something to it later, you're going to subtract now, so that when you add it later, it's the right number. Then we append the 6-bit opcode. Why 6 bits? Because MIPS has 6-bit opcode. And then we write it as hex. I'll let you ask a question on this process. This is calculating the actual bits of the instruction. Remember von Neumann's store program concept. We're going to store every bit representation of some part of the instruction. So every instruction and data value is represented as bits. When we fetch an instruction, we're actually fetching bits. They have a purpose. They're going to turn on and off different elements of the circuit. We can start to see that happening with a branch instruction. Question? Okay. So, last thing, putting it all together, which is a good recap for today. here's an example, seeing all these things happening at once, which you can put this in Mars and check it out. The only thing a little tricky in Mars, we can set the starting address at 0 or the default. But this is at an address right here, is 80,000. First question, is 80,000 decimal or hex or what? Decimal. So here's some code, and we were going to ask this. So what we want to do is find the machine code. Okay. This one came from the book, actually. So what we're trying to do is, for each instruction, write the machine code. This is written in decimal. Of course, you can write the bits, right? Op, RS, RT, RD, SA, and func, if it's what? If it's R type. Here's the I type. I type, remember, has 2 registers and a constant. How many bits constant? 16. And here we have a jump format. There's only 3 formats. R, I. There's the 3 cases right here. If it says ADI, it's automatically immediate. Branch and load word are both immediate, and you're going to say why, because they both have constants. And they also use 2 registers. All right, what's left? There's only 3. Jump. Only case for J format is jump. So you guys are all good on writing the opcodes, RS and RT and RD. It comes from the sheet. You know, T1 is going to be 9 because T0 is defined to be 8. They made it up, but 8's a very round number in binary. Why? Only 1 bit is 1, right? So the only issue that I think we need to discuss is how do you get these values, right? The BNE relative offset and the jump absolute offset. You want to give it a try? So let's do branch first. Let's look at this code. This is the same code, right? I just rewrote it here, just copied it. What does this instruction do? BNE T0 T5 exit someone. Well, let's see. Comment here, but what is exit? Exit is a label. So, first question: branch, relative, or absolute? Relative. So we have relative branch. We have to branch from what we're currently executing plus 4, right? Because we always add 4. How do you know that? Because we looked at the circuit. We take the PC, add 4, and then we're going to add the offset to that. We're asking you to find that. So we just unroll and go backwards, right? If PC plus 4 plus offset is where we're going to branch to, so where do we want to branch to? You want to branch to exit. What's the address of exit? Anybody raise your hand? Easiest question of the day. 80,024 in decimal. All right, so you can work with decimal, or you can work with hex, or work with binary. I'd say if they're giving it to you in decimal, we're good at adding and subtracting things in decimal, just stay with decimal. Okay. So here's 80,024. All right, is where we want to branch to. And then what? Where are we starting from? It's relative, right? What address? Good question. What address are we at? What is in the program counter as a decimal value?
80,012.
Yeah, 80,012. How do you know that? You're right. Because the program counter points to the instruction you're going to execute. So then that's already had a 4 added to it, so 80,012 minus 4, right? Minus where you want to go to is how much offset you need. So this is the amount of offset. This is the byte offset, okay? But what's stored inside this field? Remember, this field is automatically going to be shifted left. So when we reconstruct it, so to what we're going to store here has to be shifted right. So instead of storing 8 as the offset, you're going to drop the 2 zeros. What does that do? Converts 8 to what number in decimal? 2. Nope. 4. Yep. Because you divide by. No. This is what 2 actually. All right. It is 2. So we take 8, drop 2 zeros, goes to 2. To divide by 4. So what is the instruction? I'm just writing this as a tuple. All right. Okay. Tuple. If you're a computer science person, right? 5 is the opcode, right? And this is a constant field is 2. Can we see that over here? Yeah, 2. Can anybody see another way to interpret a relative branch? So we're executing this instruction, and where do we want to go to relative to where we're at? Thinking caps on. Be creative. We're executing this instruction, and we want to go to here if we take the branch, right? How many instructions away do you want to go? Oh, good job. There you go. So what this is saying in some ways is the number of instructions away that you want, number of instructions you want to skip. Skip ahead. Pretty cool, right? It can get a little tricky. Suppose you want to go backwards. You go -2, but it's already added 4. So it's going to be -2 plus 1, right? Because you've already added 4. 4 bytes is 1 instruction. Why is 4 bytes 1 instruction? Because every instruction in MIPS is how many bits? 32 bits. Okay, so you guys are good on this. You got to practice, but then how about this jump? Jump is what format instruction? It's multiple choice. What are the 3 choices? R, I, and J. It's a J. Can't be any easier than that. They give you the answer in the question. So here it is. We see it. Jump has op. We know it's 6 because it's given here. So this must be 26 because it's 32 minus 6. So our job is to find the jump target. Good question. Let's go back to the slide. Where does it want to jump to? Where's it, right? See, where's it? Jump to loop. What's the address of loop? 80,000. Okay. So do we write 80,000 here? And why? Because what's stored here is already, right? See, going to get multiplied by 4, so you have to store the number divided by 4. Okay. Any discussions or questions? We can see, so this is a really cool example because basically at this point you know how to design all the bits for any instruction in MIPS that we really care about. And it's the same in any other processor like I posted this weekend. The reason I post that, because real processors today still have this decision. They still want to hire people to design, now 512-bit wide special instructions. They add new instructions to the instruction set every year to accelerate certain things and make it more efficient. That's a hardware, software trade-off, time versus space, put in a new circuit. How do we do it? We change the encoding. But we can see here, this is one problem, right? We can see different types of instructions, different formats, absolute and relative. Even the most complex ones that they'll hire you today to do is some spin-off of this, is some variation of this. It's the same concepts. Okay. So let me ask this one. We saw the 2, right? Because we're skipping 2 ahead. Yeah. What number instruction are you branching to in the whole program? If you started from the first instruction was at 0, what instruction do you want to, like what line of the program, right? If each one of these has a line number, what line did you want to jump to?
0.
Nope. Because it's jump to loop. Loop is 80,000. So what line is 80,000 in this program, right? You start at 0 up here, right? And you eventually get to 80,000. Each instruction takes 4. This is the loop is the 20,000th instruction in the program. Making sense, right? Okay. I think if it makes sense to you, you don't have to memorize hardly anything. If you don't know what you're doing, you have to memorize too many things, and it just makes it hard on yourself. It's actually easier to understand it. Yeah, good.
You said that the opcode was 6 bits, but
Yes, sir.
why are we providing only 4 instead of
Okay, so say one time, so 6 bits and why what?
I was noticing it said 6 bits, but normally dividing 4. Why just 4, not all 6?
Because the opcode is the operation, and this is the operand. One is a verb and one's a noun. Right? Opcode is a verb, and this is a noun. So whatever the verb is has nothing to do with the noun. Like the opcode is a verb, right? That's over here is 6 bits. Where we want to jump to is actually is an object, right? Yeah, I didn't do good in English, right? Not that good. So, but this is the verb, right? And this jump to where? Go to school. School is the object of the sentence, right? Go to school. So this is school is represented as 26 bits. We have to convert the 26 to 32. There's a formula. It's here. We take this. We're going to shift it to, now we got 28. And we concatenate 4. And we got 32. That's why. So actually the opcode has nothing to do with it. We're all on the noun side. There's no verbiage. So here's our summary slide. You can see all the different addressing modes here. This is something to go look at and convince yourself why each one of these fields affects the thing it does. Some tell you which register you want to access. Some tell you how to get data from memory. Some are absolute and some are relative. We covered that. So we've, in this module, which is low energy, MIPS, small instruction set, and limited number of bits. Or if you're doing high performance computing, the latest chip from Intel, it's just for servers. Actually, you can't buy that for your laptop. As people were complaining there, if you read the comments, they wanted to buy that chip. Well, it's only for servers. That is the 22 cores, 28 cores. But anyway, it's the same trade-offs. For low energy, you probably want simplified decoding, a regular instruction format, which means every instruction has 6 bits opcode. Intel, they make it variable. Concise designs, the more compact we make the design, the less energy, the faster it runs. This is easier also to understand and to debug. Our instruction set is very compact. If you want to make your code fast or your design fast, you should optimize the common case. So this is inspiration for people that want to take the next class. You're going to say, okay, this is kind of cool, and I can see designing a processor and how it's done. What do people hire you to do? You can go in and do analysis like benchmarking. We already said run a workload. Go in there and tell me how many of each instruction class there is. We did that percentage. Well, from module 5, we said to make the system fast, we want to target where we're spending the most time. Well, every instruction has a CPI, is the number of clocks. So now get the number of clocks and get the percentages is telling you as a designer what you want to optimize. Remember the guy that was running from point A to point B, and he took some time to get to the start line, and then he optimized the rest of it? Well, here we can spend our time and our energy and our area on the chip to optimize where we're spending the most time for that customer. And what happens if you do that, you end up with a GPU instruction set instead of a CPU instruction set. You've optimized the gates on that chip for a particular instruction mix. That's the next course. That's computer architecture, 2 courses away. And the idea is you need some balance in that design. If it's too many of one, too much resources on one or not the other, then there's not balance. So here's the summary of MIPS instructions that we've covered here. And these should all be kind of making sense to you now. And we see these different categories. Sometimes we use category or class, right? Arithmetic, data transfer. We cover in this module, right? Logical. Branch we had in the previous, and jump we had. Okay. So what do you need to know? You need to know what the instruction does, and then also how to represent it as bits. And that's making the connection to hardware. So I'll let you guys, I'll pull up the next one, let you guys ask any question on Module 6. I think we had a good review today because this is actually that last example. If you can do the last example, I think you're in real good shape for Module 6. It's putting everything together. Wow. Yes, sir. No. Okay. Okay, let's take a look at Module 7 is procedures and stacks.